Okay. Just in the scrolls.
Okay, can I start? Okay. People online here. Everybody have to know. Right. Hello, online people. I hope should be behind me as well. Was there a chat?
Yeah. Oh. Oh, you've only got one participant. That's fine.
Ah, okay. And that so that's
Yeah.
there's no Discord on the computer.
Yeah. Did you share them?
The Discord, we couldn't get it to screen share, so we'll try and fix it next time. But there's only one person on the Discord anyway.
Okay, so all right, so it's just that. Well, thanks for the invitation to speak here. I haven't spoken in front of people for about 20 months, so it's nice to do it again in front of you guys. I was asked to say a little bit about what Galois theory is, since this is maybe the Galois Society or something like that. So, what is Galois theory? So, Galois theory is one way to try to understand equations involving polynomials. And it's an approach to doing that using algebra. Other ways, you might use analysis or geometry or computers these days, but Galois theory is an algebraic approach to understanding equations like this. So the left-hand side here is just a polynomial. I hope that that's sort of a familiar concept. We've been solving polynomial equations since early high school, for example. Okay, so what we're going to do today, just some examples of solving polynomial equations, a little bit of history of Galois theory, well, before it was called that, and then what actually Galois himself did to advance this topic. So let's start by agreeing that the numbers that we care about are just the rational numbers. So we're all familiar with fractions, ratios of integers, A over B, we know how to add them, subtract them, multiply them, and divide them. And let's just take that to be all the numbers in the whole universe. So there are no numbers other than those at the start of this talk. If you only have those numbers, you can still ask about equations like this. This is a very simple equation, of course. But let's start with it nevertheless. X squared minus 2 equals 0. So that's asking for a number, which if you multiply it by itself and then subtract 2, you get 0. I hope everybody knows that. Okay, now somebody has joined. Oh, I have to let them.
Should I turn that off?
No, that's fine. I can let you get it. So I hope all of them left us. One. Right, so I hope everybody knows that there is no rational number whose square is equal to 2. Has everybody seen that at some point in their lives? Is that familiar? Yeah, okay. If it's not, then that's okay. We don't really need it. But it's sort of curious that you can already write down such a simple equation. If you start with such a basic system of numbers, you can very easily come up with equations that you cannot solve just staying in that system of numbers. So there's no ratio of integers whose square is 2. And so you could say, okay, well, I'm done with solving polynomial equations and rationals. I can't make any progress. I'm going to work on a different problem. Or you could be sort of adventurous, perhaps, and try to extend your system of numbers. I'm going to give up on just working with the rationals and add in some new numbers, whatever that means, and however I might do that, in order to be able to solve this equation. Because for some reason, I really want to live in a world where there is a number whose squares. Maybe very important thing. So there are several ways that you could do this, that you could invent new numbers in such a way that you can now solve the equation x squared equals 2. One way would be sort of what an analyst would do. So an analyst would say, the rational numbers are useless for all sorts of reasons. And my solution to this problem, the failures of the rational numbers as a system for analysis, is that I invent the real numbers. You spend a lot of time in analysis learning about the real numbers, how they are constructed, the nice properties they have, and so on. Once you have all those nice properties, you can say, okay, here's y equals x squared in blue. How do I know that there's a number which should be called the square root of 2? Well, I can just go across and then down from 2, and I'll get to a real number, because there's no holes in the real numbers. And so there is a real number whose square is 2. And sort of formally, we would say that the real numbers are connected, and so you can apply the intermediate values or something. Don't worry if that doesn't make sense, if you haven't done that much analysis yet, because we're not doing any real numbers today. Galois theory is an algebraic approach, so we're building something else on top of the rationals. We're not building up the whole real numbers today. So what would an algebra person do? How would an algebra person say, I want there to be a number whose square is 2? Well, the algebra person would just say, shove it in there, just invent a new symbol, which I'm going to write like this, square root 2, and live with it. So I have this brand new symbol. It has no practical meaning except that it's something I can write down. And do as much of the usual stuff as you can. So if I'm going to admit this new number, which is square root 2, and I want to do all the usual arithmetic, then I need to be able to multiply that number by other rationals, which are already in play, so I can form this kind of expression. And I need to be able to add other rationals to that. And so you force yourself, if you're going to invent this symbol, you force yourself to live with expressions like this. And it turns out that you don't need to get more complicated than that. You can add two expressions of this form, and you'll get another one like that. You wouldn't need to invent further symbols for even stranger objects. And even if you multiply together two things that look like this, you'll get something else that looks like that. And you wouldn't need to invent more bizarre on top of that. And if the symbology of introducing this creature is makes you nervous, I mean, there's a formal way to do this, which I'm not going to talk about too much. But, oh, okay, so I should show that earlier. But here's that, if you force this thing to exist, then you're going to have to have this and that. And how do you multiply them together? You just pretend that you know what you're doing, and you multiply it out. And the only thing you know is that the purpose of this symbol is that it squares to 2. So when you multiply that term by that term, you'll have 6. And that contributes to that 8. Yeah. But if you don't like this introducing of the symbol, there's a formal way of doing this where you're actually just working with pairs of pairs of rational numbers. So the only purpose of writing it this way is that you sort of avoid strangely being called the square root. So don't worry too much about that really, but it's possible to do it in a more sensible way. What we've done, and we should check also that what we've done is really make something larger, not make something new. So inside this new thing, which has a square root of 2, we still have things that deserve to be called rational numbers. Because if you happen to have none of your square root of 2, then you're just still doing the usual operations of rational numbers that you're used to. And there you can verify that there is somebody in there, which is really supposed to be a square root. By the way, if you have questions anytime, just check them out. This will be quite a friendly experience. And okay, so we all know the quadratic formula from somewhere. And it tells us that the roots of any quadratic are given by this formula. So whatever quadratic equation you want to solve, if it has rational coefficients, then you can solve it. Well, sometimes you don't have to add any. You're just lucky and you can take the square root of some rational numbers. But as long as you add this creature, these are some combination of coefficients of your quadratic equation. As long as you add this thing, as long as you can take the square root of that, then you can solve your quadratic equation. And if you want to solve different quadratic equations, you'll have to add different new creatures, but that's it. So here's sort of two examples. So this is the one that we had before, x squared minus 2. If I want to solve it equal to 0, if I want to find its roots, in other words, then I have to work in this creature. And the terminology, there's some terminology at the top, the splitting field, we would call it, but this polynomial is that fellow over there, because in that fellow you can solve the equation completely as these two roots. X squared minus 4, of course, you don't need to add any new numbers. 2 and minus 2 are the solutions there, so they're already rational. So you don't need to. Okay, so that was hopefully sort of straightforward. Let's look at a cubic example that's sort of next level up in complexity. X cubed minus 2 equals 0. You could check again that there's no rationals. Its cube is 2. You can do it for squares. Doing it for cubes is the same, pretty much. And so, we can invent cube root of 2 just as we invented square root of 2. And so you end up looking at things like this. And formally, you could use triples. Let's not even look at that equation. The only thing you have to be slightly careful of is that if you want to add cube root of 2, then you actually have to add cube root of 4 as well. Because if you have cube root of 2 and you want to do arithmetic, then you need to be able to multiply that by itself. So you have to allow yourself cube root of 2 times cube root of 2, which is your cube root of 4. So you have to have that as well. Okay. But now something slightly interesting happens. Unlike in the quadratic case, when we added square root of 2, we actually automatically added negative square root of 2 as well, which is sort of the other solution of x squared minus 2 equals 0. In this case, well, we've added cube root of 2, and so we can do some algebra here. We can factor this a little bit as x minus cube root of 2 times something. But this something else, we don't know we can't solve that any further. It turns out that adding cube root of 2 has not added all the solutions of this equation, only one of them. And if we want then to solve this as well, we'll have to add even more things. But we know what we need to add. This thing over here is a quadratic. And so we look at a b squared minus 4ac and we calculate that. And it turns out that what we need, remember, we've already got that. We've already got cube root 2. What we need additionally is square root minus 3. So we can add square root minus 3, just like we add square root 2. And so what we end up looking at is a slightly more complicated object here. We have to add 2 things to the rational numbers in order to be able to completely solve this equation. If you add both of those things, then you can write down the solutions. That one, that one, that one are the 3 numbers that solve that. And so we can add that to our table of examples. Yeah, so sometimes you need to add a little bit more stuff if you want to completely solve the equation. Any questions so far?
So could you do this kind of like for n cube root, root n, for example, would you make it generalized for that?
Yeah, absolutely. So if you had x to the power n minus 2, then the first thing you would add would be n to the 2, and then you'd see what else you would need to add after that to make that work. I think in that case, you would still only need to add 2 things. So it's not sort of the worst situation where you add something and you just, you know, you don't need to keep adding things forever in that specific.
So there was a case like where it could have far more than 2, right?
Yeah.
Okay.
I'm just picking here another example. I'm not going to go through this at the same speed. Well, in fact, I'm hardly going to go through it at all, but here's just another equation, which you could try to solve. It has 4 roots, so there's 2 here because you could have plus or minus 3, and then there's another 2 there. And the right field, the splitting field in this case is that big. Okay, it's a bit more complicated. But you could do this by hand if you really wanted to, because this is a quadratic in disguise. You know, it's like y is x squared, and it's y squared minus 10y. So that's why, although it's degree 4, we can still do something. It's a bit of a, it's not the hardest degree 4 example by any means. So I just put that there for another example. Okay. So we didn't do a lot of examples, but in all of the ones that I showed you, all we ever needed to do in order to get all the solutions was to take radicals, take a radical of something and add it, and then maybe repeat that procedure 2 or 3 times, depending on how complicated things are. So it's a very difficult question for a long time to figure out whether every polynomial with rational coefficients could be found somehow in this way. So maybe first of all you add a 5th root of something to the rational numbers, and then you add a cube root of something else, and then you add a square root of some other thing. You know, depending on the polynomial you started with. But is it possible, no matter what polynomials you start with, to carry out some sort of algorithmic procedure, knowing at each stage what new radical to add, and after finitely many steps, end up in a situation where you can write down all of these. So let's sort of go through this a little bit. Degree 2, which is the quadratic like x squared minus 2 that we started with. I mean, that was a very, very old solutions to this problem, you know, 2000 BC, pretty much, in Babylonia and Egypt and China. So we're not doing algebra. Algebra didn't exist for another, well, 3,000 years, let's say. I'm not sure exactly, but anyway, a long time. So they were in some cases describing, you know, writing down solutions to explicit families of quadratics, and in other cases taking sort of geometric approaches to these sorts of things. And then later there were others as well, but these are the 3 oldest that I could find. So anyway, certainly this is very, very ancient knowledge, although they wouldn't have written it the way we write about those things today. And then so degree 3, the cubic like x squared minus 2 that we looked at, this already took a long time. Although there were some examples, families of examples of cubics whose solutions were known earlier, the sort of first completely general answer to the cubic question, the answer, by the way, is that yes, you can always construct the solutions of the cubic by adding radicals and maybe doing it again, maybe doing it again. So this was in Italy in the 16th century. So there were 2 people who sort of did it semi-independently. So I'm afraid I don't really know how to pronounce these names. So Dalfero figured this out, and Tartaglia figured this out. But neither of them really wanted to tell anybody that they had figured this out. Why would you not want to tell anybody? I mean, you just spent a long time figuring out one of the most famous and most difficult problems of that time in mathematics that people were thinking about. And you're going to keep it to yourself. So what possible reason could you have for keeping it to a set? Yeah.
I may be cheating because I know that. But basically, the Ferrari and Catania had this. They had these competitions, like mathematics competitions. Like the first who could found roots of polynomials would win, and they developed this method, so they didn't want to have a competition. So.
Yeah, that's right, exactly. So for instance, if there was a job available in some university, how would you even decide who is going to get that job? You will have a public debate, a public competition in the town square. And this would be a very major social event. Lots of people would come. It would be judged by the city mayor or the local governor or something like that. And in this public display, you would be given mathematical questions, maybe from your opponent. I don't know exactly how they worked. And you would see who would do better, who could better answer these questions in front of everybody. You wouldn't know what the questions were. And if you did better, if you won the challenge at the end and you got the job or whatever was, the prize for the contest at that time. So these guys were afraid, I think, actually, of meeting exactly each other in such a contest for some reason. And so they kept this secret to themselves so that if it came, the contest one day, they could come out with this brand new knowledge and surely carry the day because nobody knew how to do this. So that's why it was, they didn't rush out to tell other people about this, they kept it to themselves. And so there was this third guy, Cardano, who, well, it says here, so Tartaglia told Cardano his solution, but he only told him after Cardano promised not to tell anybody else, because Tartaglia wanted this for himself in case there was a challenge. Cardano presumably was already, a high status guy in the job, and so didn't maybe need to do that. I'm not sure about that. But in any case, so Cardano wanted to know. He promised that he wouldn't tell anybody. And so Tartaglia said, okay, I'll tell you how I did it. Don't publish it. And then later, Cardano learned from, I think, Dalfero's student VR, but anyway, from somebody of Dalfero's method. And so Cardano thought, well, I've learned another way of doing it from Dalfero. If I publish that, I will not have broken my promise to Tartaglia, and I can still publish, which he was very happy about. Why was Cardano so desperate to publish the solution to the cubic? Because around the same time, the degree 4 problem, which was also, circulating, people knew that they wanted to do this as well, had been solved by Cardano's secretary Ferrari, but up to the solution of the cubic. So Ferrari figured out that if I can solve cubics, then I can solve quintics. And so in order to publish this, Cardano needed a solution to the cubics as well. And so he got it from 2 people. He published the second one. The first guy was pretty angry about that. But anyway, he published it together with a quartic in this thing, I think, Ars Magna. And that was the state of the art, sort of the middle of the 16th century. They knew how to do quartics, degree 4s. Not just like the one that I showed you, which was quite special, but all of them. And that was it. So they got to quartics. And not much happened after that. Lagrange, 200 years later, sort of looked at everything that had been done and put it all on the same page, tidied up all the methods, made it work sort of the same way for all the different degrees, and things like that. And was kind of puzzled, like, why does this work for degree 2 and 3 and 4? And we don't really know what to do in degree 5. So this made degree 5, x to the power 5 and so on. Solving those polynomial equations was sort of a big question, just like degree 3 and 4. As until, well, not long after Lagrange did his work, at the end of the 18th century, Ruffini came along and said, degree 5 is not like degree 2, for example, because there is not a single formula that works all the time. In degree 2, there is this thing called the quadratic formula, and it always works. It doesn't matter what quadratic you start with, you throw it into the quadratic formula, and you get the answer. So Ruffini says, there is not a single formula that works for every degree 5 equation at the same time. They didn't know, maybe different degree 5 equations have different, maybe different degree 5 polynomials have different equations that work for them and for them. So they weren't sure about that. But they knew that there was something that didn't work universally. Ruffini had maybe a small problem in his group or something, so Abel fixed that in 1824. Abel was, I think, Norwegian. So they knew that something was going on. And then a little bit later, Galois came up with a general approach to understanding this sort of problem. When can polynomials be solved by repeatedly checking that? This is in 1830. What I want to do in the time that's left, which hopefully will be enough time, is to sort of say a little bit about what he did. Well, at least in the way that we would talk about it today. So the way that they did things was very different. They didn't have the technology that we have. In fact, Galois sort of was one of the first people to invent the technology. So it was still, a brand new thing at that point. So they've talked about it very differently from what you see in your course. These guys are also, kind of curious. They both died young, quite radical people. I think Galois died in a duel or something like that when he was under 30. So, there were different times, both for the Italians in the 16th century and wherever these people are from. I don't know where they're from. Galois, I think it's French. I don't know where they're from. Anyway, so I want to try to tell you a little bit of a story about what Galois did, or how he thought about these things, or at least how we think about what he did. And so let me sort of start with this idea. When I showed you the examples, we were adding new numbers to our rationals to make bigger systems of numbers. Q root 2, Q adjoint root 2, for example, was a new system of numbers, a new field you could add and multiply and subtract and divide. And you could also, as it happens, solve this new equation that you care about. So here's like a sort of toy example of that. It's not really connected to a specific polynomial equation anymore, but here's a bunch of things. You could start with a rational, and you could add square root 2 for whatever reason. And then you might also want to add square root 3. Maybe you're interested in having both of these numbers available for whatever problem it is that you're working on. Now, it turns out that if you do that, you of course have added in particular square root 3. So this smaller field, this smaller collection of numbers is sitting in there. So these lines, by the way, are supposed to represent containment. If you add square root 2 and square root 3, then you certainly added only square root 2, and you certainly added nothing. So this is like smallest, and that's like biggest, and you also added square root 3. But it turns out that you also unavoidably added something else. There's also root 6 in here. Of course, if you multiply these two together, you get something that should be, or could be deservedly called the square root of 6. And so these sort of pictures, not just the thing at the top, which is what you need to be able to solve the equation that you started with, but the whole picture, all of the smaller things that are in there, and all of the containment relationships between them is where, well, at least where our modern approach to Galois theory starts. So these are the sorts of pictures that you see a lot of. So let's look at one of these pictures for our cubic example that we did earlier. The picture for the quadratic is not very interesting because you would just have these two things and there's nothing in between them. You either add square root 2 or you don't. So you need a slightly more complicated equation for an interesting picture. So let's look at this x squared minus 2 equals 0 thing that we did before. So in picture form, first we added a cube root of 2, but that only actually gave us one root. So then we also added square root minus 3, and it turned out, I didn't really go through that calculation or anything, but if you add those two things, you can solve this equation. Now, of course, if you've added those two things, then in particular, you've just added square root 3. So within that is the smaller system of numbers where you just add square root 3. Sure. Okay, fine. That's agreeable. But there's actually more. There are other things secretly inside that top guy as well. There's a couple of other things. And maybe it doesn't really matter exactly what these things are. You fix your favorite cube root of 1, and then you can find it in there. And then omega squared cube root 2 is also in there. That's a smaller system of numbers. If for some reason you only care about having exactly this value, or I don't know what problem, but maybe you really like that number, well, it's in there, and you cannot avoid it. If you decide that you want to solve x cubed minus 2 equals 0, well, that's going to be hiding in there somewhere. Maybe that's not so surprising, because if you cube this, you get 2, because omega cubed is 1. But that's going to be in there. And in fact, that's all that's in there for this special example. There's nothing else over here or contained in all of those guys or anything like that. So that's the whole picture of field containments for this specific equation, it turns out. Except that there's actually more information in this picture than just the lines, which I haven't told you about before. We can put a little number on every line. And the number is roughly about how big of a gap there is between these two things. I mean, if you want to define it formally, then something upstairs is a vector space over something downstairs, and it's the dimension of the vector space, but it doesn't matter. There's numbers for each of these lines. When we add a cube root, the number is a 3. When we add a square root, the number is a 2. And notice that no matter how you go from the bottom to the top, you'll always multiply to get 6. So there's something 6-ish about that thing. So there's quite a lot of information in this picture. I mean, maybe it does not make sense, but anyway, there's a picture that we can draw, and it's got, there's lots of relationships between lots of different kinds of numbers, and things like that. So the idea, at least the way we would talk about it, of Galois theory, is that a picture like this, which let's say it's a field relationship diagram or something like that, happens to look like something from I mean, not completely different, but another part of mathematics altogether. Not that that part of mathematics existed when Galois was doing this, so again, he didn't think about it this way, but it looks like something from group theory. So to continue the example, let's look at something which apparently has nothing to do with this at all, which is the symmetries of an equilateral triangle. So here's a triangle, all the sides are the same length. And if I want to manipulate this triangle in the plane without sort of actually changing it at all, well, I could reflect it in the vertical. That will take vertices to vertices. And let's call that map tau, which reflects reflects in this dashed line. And I could also rotate it, let's say anti-clockwise by 120 degrees. Let's call that sigma. So that will take the triangle to itself. So these are two maps of the plane. You could write them down as matrices if you wanted to. And if you check what they do to these 3 points, they will permute them, but they will not, vanish or disappear or something. Now, if you allow me to do sigma on this triangle, and it will rotate, and if you allow me to do tau on this triangle, it will flip, and nothing will happen, and the vertices will be sent to vertices, then I hope you agree that if you allow me to do sigma twice, or sigma and then tau, or tau and then sigma and then tau, or whatever composition of these maps you like, the triangle will still look the same after I do. And this sort of, and so you can start making a list of all the different things you can do. Sigma, sigma squared tau, sigma tau, sigma tau, sigma tau, sigma tau. That didn't go very well. But anyway, you can keep composing these as many times as you like. But it turns out that after a while you don't get new things. In fact, you only get 6 things. you could do nothing. You could rotate it 120. You could rotate it 240. So that would be sigma and sigma squared. You could flip it, which would be tau. You could do a flip and a rotate, or a flip and a double rotate. So it would be sigma tau and sigma squared tau. And this thing that you get by doing this is a group. And so I'm going to be a little bit vague about this if you don't know what a group is. But we call this group that all the things you can do to this triangle, that's something called S3, the symmetric group on 3 points. And within that, there are smaller groups. There's this thing where if you only allow yourself to rotate, maybe you don't like reflections because they're not orientation preserving or something that you don't like. So maybe you only care about the rotations and you get a smaller collection of things. Or maybe you only care about reflections and you get an even smaller collection of things, and that sort of thing. So all the subgroups, we would say formally, of this S3 are arranged in this configuration. And the point is that this looks exactly the same as the picture for the field containment in the other slide. Well, okay, except that it's upside down. So here's sort of the outline of how Galois theory works. You start with a polynomial that you care about solving. You come up with the big field with all the numbers that you need in order to write down all its roots. So that we call that the splitting field in the table. And then you look for all the other things inside it, all the smaller collection of numbers that you happen to have added as well. And you make that complicated diagram. And then you go into your bag of groups, if you know a lot of groups, and you pull out one that has the same diagram for its subgroups. And you say, okay, these things have something to do with one another somehow. And now if you only do that, that's not very interesting. Well, it's interesting, but it doesn't really help very much. But what Galois said is that if the group I associate to the polynomial has a certain property, which I can verify by some calculation, then the polynomial I started with will be solvable by radicals. I'll be able to write down its solutions just by taking roots and then roots and then roots and then roots. So this was the sort of, compared to what Abel and Ruffini did, this was sort of the big breakthrough, because from a specific polynomial that you really care about for some reason, you can come up with this other thing in algebra, this group that you can calculate with, play around with, and verify a certain property of, this solvability property. And it has that property, then you know something about your polynomial. And this was amazing. It wasn't really even understood when Galois wrote it down, partly because what he wrote was a bit of a mess. And it took a long time so he sent it to the Paris Academy and they were like, we don't understand this at all. And so it took a while for the establishment to sort of understand what it was that they'd done. But in the end, it was understood that this is really intuitive. So I don't know if Galois knew exactly this, but from what Galois did, we can have a theorem like this, which is that this specific polynomial, so here's just another example, we could have thought about it in the beginning. You cannot write down its solutions, so that you expect there to be 5 solutions, to be 5. You cannot write them down using square roots and cube roots and fifth roots and repetitions of those things. To me, that's a bit strange. It's kind of amazing. But that's how it's. So I can go into this maybe a little bit if people are curious, why should that be the case? I'm not really sure how familiar people are with the idea of a group. But that's more of that. So let me just leave you with a question, and then I hope you will have questions for me. Although this was done, although what Galois did was 200, 300 years ago, whatever it was, there are still things we don't know about this approach. You start with a polynomial, you do some business, you get a group. Okay, fine. So if you know what a group is, people still don't know the answer to this question. pick your favorite finite group. If you've been doing group theory long enough, you have a favorite finite group. Can you come up with a polynomial that will give you that group exactly and not a different one when you run it through this machine? When you say, okay, turn the crank and get from the polynomial to the group. Now, people know a lot of things about this question. There are lots of groups that are known to appear in this way, but we don't know every group does. So that's kind of neat. Anyway, thank you very much for your attention. That's the end of the talk. Yeah, so if anybody has questions, I think I'm happy to try to answer them.
I have a question. Maybe it's a bit trivial though. So, but what do you mean exactly by group B? So,
Oh, okay. So every group has, there's a way to make, so you start with a group, it has a lot of subgroups. There's a special subgroup called the commutative subgroup. It's generated by all the commutators, which are things like A, B, A inverse, B inverse. If you've seen that, you know what that is. And so you can take a group and then you can look at its commutator subgroup. That itself is a group. So it has its own commutator subgroup built up of commutators of things from that. And you can keep doing that and you can keep doing that. And if after doing that finitely many times you get to the trivial subgroup, then the group's solved. That's the definition. It's not very, I mean, why? Yeah, that's the, I don't think that helps to know why the theorem is true, but that's what it is. Yeah. Any other questions? Oh yeah.
I was going to mention when you kind of go through the history and the timeline of like Galois theory, like there's like to solve polynomials like through iteration, also like the Newton-Raphson method, you could use that as well, couldn't you? Like for solving polynomials. Is that something? What is it different to this approach?
Yeah, I
Is
think,
it
yeah.
similar?
I think that would fall into sort of the analysis approach of things, where you're trying to get as close to the solution as you can in like say you know, a decimal expansion sort of sense. So that would be where you like real numbers and you want to say, I want to know, you know, the 100th digit of cube root of 10 or something. And so the Newton-Raphson would let you start with an iterative procedure, which will stay within the rational numbers, which is good because you can calculate those in a computer relatively easily, and we'll get more and more accurate with some maybe even explicit thing that will tell you I only have to repeat this 10 million times if I want the third digit of something. Hopefully it's fair. Yeah, so that would be like an analysis. There's nothing wrong with that.
that's another one.
Okay.
Oh, sorry.
I'm not, I have a question.
So you mentioned the meaning of the numbers on the arrows in the diagram. But you did that for the splitting fields, but not on the group.
I didn't put it or I didn't mention it.
Yeah, no, like you explained the meaning of the
yeah.
sort of dimension in the splitting field diagram. When you also talk about the S3 group, they also have these
Oh
numbers,
yes.
but I'm not sure what they mean in that context.
In that context is, I think, simpler. So whenever you have a line, it means that the thing in the bottom is inside the thing in the top. And the number on the line is just the size of the thing on the top divided by the size of the thing on the bottom. They're both finite sets. So they both have cardinalities. And it's just the ratio of the cardinalities. In group theory, it's the index of the subgroup in the group. But yeah. I should say also that when I showed you a field containment diagram and put numbers on it. And then I showed you a group containment diagram and put numbers on that and said these two things must be connected. It turns out that, so that was a bit of a cheating way to sort of introduce this, because two different groups could have the same picture. And so that's not really how people go about picking a group. They don't look at the picture and say, oh, okay, it must be that one. There's other ways to do it. But hopefully it's okay. Let's see what it's doing. Okay, well, we can stop there then. Thank you very much for coming. Oh, yeah.